Alright, what up fam? Here we go on this mod 7.1 to 7.3 review packet. This first page, not going to focus too much on it because we're going to have to repeat all this material again later, but we'll briefly mention a couple things. So first of all, these guys here, it says domain first. We'll do domain at the end. We actually want to do that later, so we're going to go straight to this vertical asymptote idea. So vertical asymptotes always occur when the denominator equals 0, so long as the numerator does not also equal 0. In other words, when there's not cancellation of some kind. Let's go ahead and check out this first one then. So if the denominator is going to equal 0 when x equals positive 5. Easy enough, really not that hard. If I plug in 5, I'll divide by 0. And again, my thought process there is if I plug in a number very, very close to 5, perhaps on the left-hand side of 5, for instance, if I were to plug in x, make it equal to 4.99999, like that, if I plug this in here, subtract a 5, I'm going to end up with negative 0.0001, just like so. Maybe one more 0. I'm not really counting right now. It doesn't matter to me too much. It is actually one more 0. It actually does matter to me. I lied. Okay, so, or is it one more 0? No, it's not. Oh my gosh. Whatever. Point is, if I have this number, I'm doing 1 divided by that number, I'm going to get negative 10,000. It's going to be huge. Because I have a negative 10,000 here, it's going to go all the way down to negative infinity. Whereas if I plug in a number on the other side of this x equals 5, maybe 5.0001, that's going to give me x minus 5 is going to be 0.0001. And it's going to be positive 10,000. Effectively, there is this asymptote in this question where you're going on the left-hand side of 5 here, you're going down to negative infinity, and you're going all the way up to positive infinity on the other side. This will happen anytime I have a multiplicity of 1 in my denominator for one of my asymptotes. Really not too big a deal. Please note the vertical asymptote also functions as a place where your domain cannot be that number. You're not allowed to plug in 5 into this function. So what we're going to say is we're going to say ARN for all real numbers. You could also write this fancy little R right there. Also stands for all real numbers. Except x is not equal to 5. Or x cannot be 5. In other words, all real numbers, x not equal to 5, or except x equals 5. I don't know, something to this effect. Don't really know if that's going to be on the quiz or not, but some version of that domain is there. Horizontal asymptote, by definition, is what happens as x goes to infinity, what happens as x goes to negative infinity. There are a couple of rules of thumb we can follow for our horizontal asymptotes if you want to, but you really want to think about what happens if I were to make x extraordinarily large. And in this problem, if you made x extraordinarily large, say a billion, I'd have basically 1 divided a billion, I don't know how many zeros I'm writing, I don't really care, minus 5, and this is going to be approximately 0. It's just so small. Plug it into a calculator, you get 0.0000000. It's a really, really tiny number. Or in other words, my horizontal asymptote is the line y equals 0. You could go through this thinking process for every single one, but my students tend to like memorizing stuff, so I'm going to go ahead and make up a little sheet right at the start here. We're going to go back over to this guy. General rules of thumb for your horizontal asymptotes. Feel free to skip this part if you know how to do horizontal asymptotes, by the way. But if you don't, horizontal asymptotes are always going to be these dotted lines of y equals a number of some kind. If there is a horizontal asymptote, we're going to figure out some questions later when they are not any horizontal asymptotes, and the only effect at the edges of the graph. So in other words, no matter what my graph is happening, perhaps there's a 0 over here, I don't know, whatever that guy is a 0, the horizontal asymptote is only going to happen after that last 0, or it's only going to happen after the last asymptote. You will always be approaching the asymptote either from above it or from below it, one of the two, so it's either there or there or there, one of these guys. So it's only going to be one of these two or one of these two, and you're going towards that asymptote. In order for us to truly just get to the nitty-gritty of it, all of our rational functions are going to be equal to a polynomial over a polynomial. And if you have a polynomial over a polynomial, you will have a leading term of that polynomial. And you'll have a leading term in this polynomial. So I'm going to quickly make 3 different examples that show us the 3 different situations you could be at. We're going to create f of x equals, and let's say 2x cubed plus 3 over, I don't know, 5x minus x cubed. And then we're going to have another one. We're going to do g of x, and we're going to say this guy is equal to, how about 2x cubed plus 3 divided by 5x minus x squared. And then we're going to do h of x, and we're going to say that is 2x cubed plus 3 divided by 5 minus x to the 4th. So I picked this on purpose, where all of them have the same guy up top, and the only difference on the bottom is the exponent I have chosen for my x. So we're going to take the leading term from these guys, and we're going to compare and contrast those leading terms. In this first one, the leading term over the leading term is this. And effectively, these guys cancel out. So why are we looking at these leading terms only? Well, if you were to plug in these enormous numbers, these billions, as I was talking about when you're going over on the left and the right-hand side, basically, these guys don't matter. This 3 is irrelevant. This 5x is irrelevant. If you compare a billion cubed to just a billion cubed, I mean, how many zeros are you going to have on this thing? You're going to have 27 zeros on this number, compared to a number that has 9 zeros. This number just overshadows it. So we just ignore anything that's not the leading term. If you cancel these guys out, you're going to get -2. And in fact, that's all it is. They're 2 over -1, which is -2. And so we'd say the horizontal asymptote is y equals -2. In fact, this is one of our rules. If the degree of the numerator, you're comparing the degrees of these guys. If the degree of the numerator, which I'm going to call n, equals the degree of denominator, called d, so n equals d, you compare the coefficients. In this case, 2 divided by -1, which is going to be our -2. In this problem, it's a little bit different. If we were to do this instead, we're going to have 2x cubed over -x squared, and we try to cancel everything out. That's going to give us ending up -2x. This is no horizontal asymptote compared to this y equals -2 horizontal asymptote. No horizontal asymptote. And when there is no horizontal asymptote, you're going to revert back to this little chart that we did last chapter. For those who don't remember, I'll try to remind you, this is for our positive, this is for our negative, and this is for our even, and this is for our odd, and we're talking about the coefficient in front over here, the degree over here. In this problem, we have a negative odd. This is a negative odd, so this is our end behavior right there. In fact, we could talk about horizontal asymptotes purely as these end behavior situations. Last but not least, comparing this last one over here, 2x cubed over -x to the 4th. If we were to reduce this down, get 2 over -x. And if we were to plug in some extraordinarily large number, just like we were talking about earlier, this is going to be y equals 0. So in fact, anytime your numerator is greater than denominator, you have no horizontal asymptote. And anytime your denominator is greater than your numerator, or maybe your denominator greater than numerator, y equals 0 is your horizontal asymptote. So there's your little horizontal asymptote lesson. Let's go back to this guy over here. And that's where we got this y equals 0. I'm going to go ahead and cover problem number 3. The reason why I'm covering problem number 3 is so that we are able to practice some factoring here. Actually, I lied to you. I'm problem number 8. I like number 8. 8 has extra factoring here. We got lots of factoring on number 8 here. So number 8, always got to factor first if we want to look at our vertical asymptotes. But let's do our horizontal asymptotes first because we just remembered that one. Our horizontal asymptote is y equals 2 over 3 because we're doing the x squared over the x squared coefficients. But to do the other stuff, we got to factor that top and bottom. So we got to check to see if there's any cancellations, anything special like that going on. So factoring this guy, we're going to have to multiply 2 multiplied by -9. That's going to give us -18. Now we have to ask ourselves what multiplies to -18 and adds to +1. So our choices are 1 times 18, 2 times 9, 3 times 6, 4 times nothing, 5 times, oh, not factorable. This one's not factorable. Maybe I should have chosen this guy up here for factoring. We'll go back to that in a second. But this denominator does factor. We can pull out a 3x squared minus 4. After that, difference of 2 squares, and that's going to be 3 multiplied by x minus 2 times x plus 2. And therefore, our vertical asymptotes are at x equals 2 and x equals -2. What makes that denominator equal 0? And likewise, our domain, all real numbers except x equals 2 and -2. I think this one is factorable, so let's just check the factoring on this for those who need the factoring help. So factoring help here, we got 2 times 4 equals 8. What multiplies to 8 adds to 9? Ah, this one can. 8 and 1 both work out nice and neat. So we can rewrite this as 2x squared plus 8x plus 1x plus 4. Again, that 9 became the 8 and the 1 that you figured out earlier. Finishing this off, we're going to squiggly line it down the middle. Factor out from the left, 2x times x plus 4. Nothing can factor out here, so we're just going to pull out a 1 times x plus 4. Finalizing that factoring, x plus 4. What's left over? 2x plus 1. Easy enough. All right, moving on to the next page. I'm sure we'll see a lot of this stuff again. Any of these that I really want to try right now for any explanations? Nothing that I'm noticing. Maybe there's going to be some more interesting ones later. Find the vertical and horizontal asymptotes for the graph of these functions. Ooh, so these ones are actually given to you, and you got to work backwards. I like that. Well, here I think we have obvious horizontal asymptote of y equals 0. That's what the function is approaching as it goes to on both sides here. Whereas on the vertical asymptotes, there are 2. 1, 2, we have x equals, looks like +1 and -1. Here, horizontal asymptote, in my opinion, it's obviously none. And vertical asymptote is x equals 0. Remember, the y-axis is the line x equals 0. So this one looks a little bit more interesting. Where does this vertical or horizontal asymptote appear to be? It looks like it's right there, in my opinion, which is approximately y equals 2. And it looks like our vertical asymptote's about right there. I have no actual proof of this, but x equals -3. All right, happy enough. Let's move on to the next page. The more interesting questions. How to graph these accurately. So important. Got to practice it. Got to do it nice and neat. Step 1, always factor first. The reason why we're factoring is simple. There's a possibility of cancellation. When there is cancellation, you have holes. So let's look at it. Factoring this numerator here. I'm going number 18, by the way, because I think this is a better problem. So factoring this numerator, we're going to have x plus 3 multiplied by x minus 1. What multiplies to -3, it adds to +2. The denominator here is going to factor into x minus 1 times x plus 1. That's a difference of 2 squares. Immediately, what that means is our x minus 1's cancel. This creates a hole at x equals +1, the root of this situation. Furthermore, holy moly. Oof. So furthermore, that hole also is not part of our domain. So we're going to have our all real numbers again, except x equals 1. And let's take care of it right away. X equals -1 as well. You can't have that. And by the way, that x equals -1 is our vertical asymptote. Easy enough. This function now effectively becomes x plus 3 over x plus 1. In fact, it'll look identical to it except for an itsy-bitsy hole at x equals 1. We can now graph the rest of this thing, or at least talk about the rest of this thing, end behavior as x goes to infinity, as x goes to -infinity, f of x goes to, f of x goes to. And in this case, because the degrees are the same, 1 and 1 for both degrees, and the coefficients are 1, this guy is simply going to become x over x, which is 1. It's going to go to y equals 1. Y equals 1. Again, that horizontal asymptote is only going to happen at the edges of the graph, so we're not going to graph it just yet. End behavior near the asymptote. I don't even know what they're really asking. Maybe one from above or one from below, but I don't really know what they want there. You know, maybe we'll come back to that. Let's see. End behavior near the vertical asymptote. Yeah, I don't know what they want. I think it's going to help us graph at the end. I'll show you guys what I'm wanting on these guys. So we got our x-intercept. X-intercept is quite simple. It's the same thing as a root, by the way, as a 0. And in this case, it's going to be when the numerator equals 0, or in other words, x equals -3. Our y-intercept, what happens when you plug in 0? If you plug in 0 into this function, it will simply be 3 divided by 1. So y-intercept is going to be a coordinate, 0, 3. In the horizontal asymptote, we just talked about that end behavior, y equals 1. Now that we have filled in all this information, we want to go ahead and graph up as much as we possibly can. So we have this y-intercept at 0, 3, 1, 2, 3. We have a 0, an x-intercept at -3, 1, 2, 3, negative. We have a vertical asymptote at x equals -1. And after the last 0 or asymptote on either side, we're going to have the horizontal asymptote. So the horizontal asymptote is going to be here on the right-hand side. And it's going to be here on the left-hand side. Note how I left a gap in between those because the horizontal asymptote only occurs after the last 0 or asymptote on either side. The rest of this question is pure logic. So here, end behavior near asymptote, I think what they were trying to say is, does it start above this y equals 1 or does it start below y equals 1? I'm more interested in the logic version of it, actually, because you can only start above or below it. However, there are 3 rules of logic you always have to follow. These 3 rules of logic are going to be, number 1, you can only cross the x-axis where we've marked it. So I cannot cross this line anywhere except for here. And I have to cross right there. Rule number 2, I cannot cross any of the dotted lines that I've drawn. Rule number 3, gotta pass that vertical line test. I cannot draw something that's not a function. So, in this question, if I decided to start down below here, I would either run into the dotted line here, run into the dotted line here, or run into the x-axis here. None of those are possibilities, so I must be above the axis. Furthermore, I also knew it had to be above the axis because I knew I had to go through this coordinate over there. 2 ways of logic to figure this out. Boom. After that, on the other side, we're going to go ahead and hop all the way down here. Just like I said in the very first page, you're usually going to have this where one side goes up, one side goes down. You could analyze this by plugging in a number on the left-hand side of a -1 or the right-hand side of -1. But the easier way to think about it is it's positive over here and negative over here because this here is a single multiplicity. So we're just going to go ahead and hop all the way down there. Now you have to ask yourself the question, where does the function have to go? Well, it has to go through that axis, and it has to go towards that vertical asymptote, or horizontal asymptote. That problem's all done. Let's go to the next page. We're going to do both of them on the next page here. Just because this one's more interesting here, I'm going to do number 20 first. So again, you have to factor first. So we're factoring first. We factor out a 3 multiplied by x plus 2 divided by. And now factoring this, what multiplies to -8 adds to -2. That's going to be x minus 4 multiplied by x plus 2. Oh, we got some canceling again right away. Kaboom, kaboom. We got a whole at x equals -2. And that reminds me, I forgot about the whole on the other side. I just failed my own question. Boom, 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 we're going back. Forgot a whole. Whole at x equals 1. Look how simple this is. Put a little hole there. Okay, that's it. All right, moving back. Sorry. Okay, now we're back to number 20. We had this x equals -2. And again, our all real number domain. I'm using the all real numbers instead of that big R just for sake of changing it up. except x equals to -2 and x equals 4. End behavior. Well, in this problem, we have a 3 divided by x minus 4 as our effective function. Degree of the numerator is 0. Degree of denominator is 1. Therefore, we are going to y equals 0 as our horizontal asymptote. So as x goes to infinity, f of x goes to 0. And as x goes to -infinity, f of x goes to 0. X-intercept, none. Our numerator never equals 0, so we're not going to have any x-intercepts. Please note, when we graph this thing, it is never allowed to cross that axis. Ever, ever. Y-intercept, instead, if we plug in 0 into this thing, it'll get 0, -3/4. Alright, it's a little bit of a weird number, but there it is, -0.75. And our vertical asymptote at x equals 4. We have all this information down. Let's graph it up. X equals 4, 1, 2, 3, 4, dotted line. Horizontal asymptote. Horizontal asymptote only occurs after the last 0 or asymptote. There's only one in this problem. So it basically is this entire line actually is a horizontal asymptote. This whole thing. Very rarely does that actually occur. And we have the 0, -3/4. And really, that single coordinate on this problem kind of solves the entire question for you, because you have to go through that and you can't cross these lines, so it's got to look like this. Boom, going all the way up, just like so. Really not too much to it, and again, I really don't know what they want here. I apologize, maybe some other teachers teaching it that way. I'm just not into that kind of thing. Yeah, let's see. Is there one where it doesn't have an asymptote, horizontal asymptote? There isn't one where it doesn't have a horizontal asymptote. I'm just going to make it my own function, you know what I mean? I'm just going to go ahead and change this problem to make it so it does not have a horizontal asymptote. I'm just going to go ahead and tack on a -x out here, just so this one doesn't have a horizontal asymptote. It is going to change the entire problem, so if you've already done this one, I apologize, but I want us to be able to think about all these things when we're doing these problems. So again, you got to factor first. We got this -x multiplied by x minus 3 multiplied by x plus 2. Factor in that denominator. It's going to be x minus 3 multiplied by x minus 1. Cancel, cancel, boom, whole. X equals 3. I forgot about the whole again. I'm going to fail my own test. X equals -2. Where are we at? Boom. Okay, whole. Easy enough. That's all you got to do. Anyways, going back up here, we got this whole x equals -3. Horizontal asymptote. We just talked about how there's none because the degree of the numerator is greater than degree of the denominator. Vertical asymptote, x equals +1. Domain, all real numbers except x equals 1 and x equals 3. Please note, I've been writing it this way. There are a lot of other ways to write domain. I want to show you guys the 2 fancier ways just so you can see it at least once. And before we do that, I did promise 2 shout-outs in this video. So shout out to my first period kiddos, Reese, and for some reason he wanted me to mention him as Uncle Rico. I don't know why he wants to be called Uncle Rico, but there's his name right there for you. Second student who wanted to be called out in this video is Kira, who is pretty bomb on the ukulele, but plays the ukulele during class sometimes. I don't really know what's up with that, but anyways, here we go. Back to work. X is an element of the reals such that x is not equal to 1 or 3. This is the fancy way of writing. This is called set builder notation, and it's the way you actually would write your domains if you ended up writing fancy schmancy math proofs in your later future. If you end up in your future life in a calculus course, you'd actually be writing this differently. Effectively, when you're doing a calculus course, I'm going to draw this as a number line here. You have this x equals 1 here, and you have this x equals 3, and really you're allowed to graph anything on this entire line except the values of 1 and 3. So you can have any number in between here as written, which is going to be -infinity, 1, parentheses, union, parentheses, 1, 3, union, 3, infinity. A little bit extra, but that is the fancy way of writing this notation. Remember, the parentheses mean you can never reach it. You can never actually reach infinity, so you're always going to have parentheses, and we specifically cannot be 1 or 3, but we can be all the numbers in between. There's also another idea here. If I were to draw this number line for this problem, for instance, there'd only be one thing there. It'd only be a single little positive 4 there. And this lets us pick signs out. If it's above the axis over here, it's a positive. If it's below the axis, it's a negative. But we kind of already knew that because it was a single right here, this x minus 4. Whatever. Going back up to actually finishing this question. Sorry it's taking so long. End behavior as x goes to infinity. F of x goes to, as x goes to negative infinity, f of x goes to, well, we don't have a horizontal asymptote, so what do? Well, we actually have to go back to this leading term idea. We got negative x squared here. We have positive x on the bottom as our leading terms. Once we've canceled out, if you didn't cancel out, it would have been negative x cubed over x squared. You get the same exact thing. Either way, this is going to cancel out to become negative x, which is a negative odd. A negative odd, hopefully from last chapter, you remember it's looking like this, or in other words, as x goes to infinity, f of x goes to negative infinity, and as f of x goes to negative infinity, f of x goes to positive infinity. As you go to the right, it goes down. As you go to the left, it goes up. There you have it. End behavior near asymptote. There aren't any asymptotes in this question, so this problem is like truly meaningless now. Our x-intercept, we got 2 due to what I added. We got x equals 0 because of that guy. We got x equals negative 2 because of that guy. And our y-intercept, if we plug in 0, well, if the x-intercept is 0, the y-intercept better be 0 as well. If you plug in 0, you're going to get 0. All right, let's actually do the question. So we got 0, 0. We just marked that up. We got another x-intercept at x equals negative 2. Our horizontal asymptote, we do not have one. Vertical asymptote at x equals positive 1. All right, now starting this question off, we really just need to use pure logic yet again. We're going to start with this end behavior. We know that as x goes to infinity, f of x goes to negative infinity. So now the graph like ends up over here. And then we have to ask ourselves, what has to happen? We are not allowed to cross this axis. We are not allowed to cross this dotted line. So where do we go? Well, we got to go towards the axis. Boom, easy enough. After that, we're going to hop all the way up here. And again, we only stay on the same side over here if it is a double on this asymptote, and it's not a double on this guy. So coming on down, we're going down. We have to go through the 0, and we're crossing through. Why are we crossing through? Because single. We have to go back up to this guy. Why? Again, single. And then where are we going? Well, as x goes to negative infinity, it goes to infinity, so we're shooting all the way up. This is probably a little bit more smooth in real life if you were to actually graph it, but, you know, there you have it. Hopefully this video was informative. If you want more practice, come on by to After School Tutoring. And, yeah, have a great rest of your night. I'm going to go catch the end of the Super Bowl. I really hope the Rams are winning because I don't like Tom Brady. So, anyways, peace out, guys.